Hello students, in this video we are going to discuss the last power model in the architecture level is abstract statistical power models. As we know that in the architecture level we have different types of blocks such as adders, multipliers, memory, shift and registers and so on, right? Each block has inputs and outputs. The number of inputs and outputs depend upon the bit length. If it is 2-bit means the number of input conditions are 4. If it is 3-bit means the number of input conditions are 8, right? So if we have the internal nodes, then also number of input conditions get increases, as I have discussed in your gate level simulation, right? So this is my gate, right? So internal nodes means I am taking, this is one of the internal node. For example, the number of internal nodes get increases. What happens? The number of switching activities also get increases, power utilization will be more. So if the input bits are 2 means, so total number of input combinations are 4. You know that 2 to the power of 2 is equal to 4, isn't it? 2 means number of bits, right? So if it is 3 means the number of input conditions are 8, isn't it? So as the bit length goes on increases, your input conditions is also increases. What happens? So power utilization will also be more. So it is highly impossible in order to estimate power in the gate level analysis. So in architectural analysis we can easily determine, so using power models, not only the power models in the architecture levels. So we are going to take some decision before the power estimations, such as how many ALU is required, whether memory is required or not, and not only that one, whether it is a series and parallel processing. Like that we have to take decision in the before estimating the power in the architecture level. So based on this major decisions we can easily estimate the power, because we are deciding whether the serial or parallel processing or whether ALU is required or not. We can minimize there itself the number of components and number of switching activity. So the total power dissipation automatically get reduces. So like this, for example, in the 32-bit adder or multiplier, right? As I have discussed here, the same thing. So they are taking one example. If it may be an adder or multiplier, the input bit is 32-bit means. So totally you will get billions of input combinations. Billions of input combinations. So if it is memory means, we will get thousands of addresses. Not only thousand, it depends on bit length, whether it is a 2-bit, 3-bit, 4-bit, 8-bit or 16-bit or 10-bit and so on, right? So the number of addresses increases and data combinations increases. So the speed of simulation slowly reduces as the bit length increases, right? So because the number of events is also in, it is highly impossible to compute in the gate level simulation. So instead of doing this one, what we are going to do in the architecture level, we are using the statistical power analysis. How we are doing the statistical power analysis? In these models, they are considered average switching probabilities, right? There we are considering number of switching activities, right? So number of operations, but here we are not considering directly like that. So here we are considering the average switching probabilities, operation frequency, pin toggle counts, input and output activities and so on. So if we are considering like this, the speed of computation increases, and it is also very simple. So it is good enough for design explorations. Okay, so one more thing is, if we are considering with respect to the components, right? So we are considering different components in the blocks, isn't it? So for each component we have to use different power models. Why we should have to consider different power models for different components? Because each block, a working operation is different, right? For example, adder. The what is the adder application? We have to perform addition operation, right? So we have to perform addition operations. If there is any carry exist, I have to pass to the next MSB bit, right? So in additions, it depends on the carry propagation. In multipliers, it depends on partial products. In memory, it depends on read and write address patterns. So I can't use single power model. I can't use single power model for different components or different blocks, isn't it? So if we are using single power model for all different for different type of components, what happens? I will get error result, right? I won't get the exact actual result, right? So it should not matches with our real time result, right? So here, in the architectural power analysis, the drawbacks are, as I said before, the advantage is it is a robust, and it is very simple. We can determine the power analysis, but it should not match with our real time result. For example, um, in my real time memory, it is a random, right? So but while I am designing the model, I won't consider the random, or vice versa. In my real time it is a sequential, but while I am designing the memory, I will consider as a random. What happens? I will get the wrong result. It should not match with the real time power analysis of the memory, right? So in order to match your real time result, means your assumption should be matches with the behavior of real time memory, then only you will get the accurate result. So we can't assume every real time behavior in our model, right? So because of this we won't get the accurate result. So less accurate, less robust. So it is, as I said before, it depends on the statistical assumption. If your assumption is wrong, you won't get the exact result, right? So but even though in the architecture level power analysis based on the major decision, as I said before, whether ALU is required, whether memory is required, whether pipeline architecture is required, based on that major decision, we can able to get relative accuracy. We can't get absolute accuracy in the architecture level power analysis. I hope you can able to understand this concept. In the next video, I will discuss Monte Carlo simulation. From the exam point of view, it is very, very important. Thank you.